Solving systems of equations, special case solutions. You might remember when we were solving equations, there were a couple of different kinds of special case solutions. And these special case solutions happened when the variables canceled out and then the resulting equation was either true or false. And when it was a true statement of equality, that meant that there were infinitely many solutions because any number you plug in will make it true. And if it was a false statement of equality, that meant there was no solution. Nothing you plug in is going to make the statement true. So let's take a look at the equation we have here and see what happens. The first thing that we're going to do is distribute this 3. So 3 times x is 3x, and 3 times negative 4 is negative 12. So I have 3x minus 12 equals 3x minus 12. And to solve an equation, we want to isolate the variable. So basically, we want all the variables on one side of the equation and all the numbers or the constants on the other side. So I'm going to subtract 3x from the right side of the equation so that this is my constant side and then the variables will be on the left side. So I subtract 3x from both sides of the equation. 3x minus 3x cancels to 0, leaving me negative 12 equals 3x minus 3x cancels to 0, leaving me negative 12. And here I have a true statement of equality. So this is actually infinitely many solutions. Or we would say that x is all real numbers, or we could say that x is an element of the set of all real numbers. And in set notation, all x's such that. So those are the ways that we can describe infinitely many solutions. If we look at this equation, we have 3 times the difference of x and 4 is equal to 3x minus 4. So when we distribute that 3, we get 3x minus 12 equals 3x minus 4. And if the first thing I want to do is try to move that x value over to the left so that all the variables are on the left side of the equation, I have to do that using the subtraction property of equality. When I do, 3x minus 3x cancels to 0, leaving us with negative 12. And 3x minus 3x cancels to 0, leaving us with negative 4. Does 12 equal negative 4? No. Since that is a false statement of equality, there is no solution. In set notation, we would say all x's such that, that's probably not the best way to do this because it's really a set that has no elements in it, so it would be a null set. All right, so we're going to talk about special cases with systems of equations. And systems of equations also have either infinitely many solutions or no solution. So I'm going to solve this particular system by substitution. So I'm going to take this top equation and I'm going to isolate y. So I have 2x minus y equals 10. I'm going to add y to both sides. And I have 2x equals y plus 10. And then I will subtract 10 from both sides of the equation. And that gives me 2x minus 10 equals y. Now I have isolated y, so I have an equation that equates y in terms of x. So I'm going to take the expression that represents y, and I'm going to substitute it into the other equation, not the same equation I got it from, but the other one for y. So I'm going to have 6x minus 3y, which is 2x minus 10, and that is equal to 30. So I have 6x, and then I'm going to distribute my negative 3 to both terms. So I have negative 6x plus 30 equals 30. Now we combine like terms, and 6x minus 6x actually cancels to 0 and leaves us 30 equals 30. Now we took the expression that represented y and we plugged it into the other equation, not the same one we got it from. So this is a valid indication that there are infinitely many solutions. Why are there infinitely many solutions? 2x minus y equals 10. This is the top equation. We are allowed to multiply both sides of an equation by the same value and keep it equal. So if I use a scale factor of 3 on both sides of the equation, I get 6x minus 3y equals 30, which is the same as that second equation. So since both equations basically represent the same line, every single point on that line is a solution. And since there is no limit to the number of points that are contained in a line, there are infinitely many solutions. So we solved this correctly. We used substitution, we isolated y, plugged it into the other equation for y, and then continued to solve. Our variables canceled out and left us with a true statement of equality. So the solution is there are infinitely many solutions. And we can see that on the calculator as well. So I'm going to start a new document, add a graphs page, and enter my standard form equations. So we had 2x plus 1y equals 10. And then we had 6x plus 3y equals 30. Oops, I typed an x in. Don't need that. So I'm going to come up here, fix that problem, and hit enter. And you should be able to see that both lines are graphed in the exact same place because they represent the same line. So every single point contained in that line is a solution to the system. Therefore, there are infinitely many solutions.